Alright guys, if you're really struggling with this energy of electrons lab that you did this week, I'm going to try to assist you in the calculations and working through what it was you actually saw. So our setup was pretty simple. We had our meter stick that was lying along the back wall here. Then you had a meter stick that also went perpendicular to this. Let's see if I can get that to show up on here. So we had another meter stick that was lined up here. The reason we chose the meter sticks was so that we could actually record some distances pretty easily. You had your diffraction grating set up. Somewhere down here, so that you could look through it. And then you also had your single slit, so we had that cardboard down here. The first distance that you have to make sure you do have in your data is the distance between the diffraction grating down here and the distance to the slit up here. So you've got to make sure you've got that recorded somewhere, somehow, and we represent that with the letter Y, okay, because it lies along our Y-axis. The second value that you need actually comes from looking through the diffraction grating. So you took your little eyeballs and you put them as close as you could to that diffraction grating, you looked through it, and what you saw was that the light source, let's say you were testing strontium, so you had a light source back here that was emitting kind of that red flame. Okay, there's the fire, enjoy. When you looked through it, that light actually got divided, through the diffraction grating into its component colors. So what you saw maybe was a blue color somewhere over here. Okay, so you got a photon that was in the blue spectrum. When you're looking at light, light actually travels in a straight line path. So the light to you looked like it came from straight behind the meter stick area. That's why it looked kind of goofy. So what that's given us is actually our values on both sides. In theory, the two distances, x1 and x2 should be exactly the same, but they probably aren't because we know how we do lab, right? Things happen, human error. Maybe those meter sticks weren't exactly perpendicular. So you have to take the average of those two values for each wavelength of light that you're seeing. Okay, so for each color band, up to 2. Once you have your average value, that's going to represent the X average for our right triangle that we've made here with the meter sticks. What we're really after is that angle of the diffraction for that photon. We're going to call this angle theta. The Bragg's equation tells us that the wavelength of a photon is equal to the diffraction grating constant multiplied by the sine of our angle theta. Sine of theta, for all you math gurus, we learned that sometimes we remember some things and other times we remember very little. The sine of theta, remember, is just a trigonometric function. It's the ratio of the opposite side over the hypotenuse for a right triangle. So our opposite side in this case is x average. Our hypotenuse in the lab, we call that z. So we're going to have to actually calculate, in order to calculate the wavelength of that photon using the Bragg equation, we're going to have to actually calculate z. So z is the hypotenuse of a right triangle. You know the Pythagorean theorem. So z should be equal to x average squared plus y squared raised to the power of 1/2, or taking the square root of that value. So that's going to give you your z. Now that you have z, which is the hypotenuse, we can use our sine theta equation. So the diffraction grating constant is the same for everybody. It's 1 divided by 530. The unit on that is millimeter. You're going to multiply that. Let's see if I can shift the screen. Look at that. I'm getting fancy. So 1 over 530 millimeters times the sine of theta. Now keep in mind, when we're talking about the sine of theta, it's really multiplying by the ratio of the opposite over the hypotenuse. So in this case, 1 over 530 millimeters times our opposite side to theta is x average divided by z. Note that your final unit is going to be millimeters. Typically, when we're talking about the visible spectrum, we want to have that in nanometers. So we want to be able to go from millimeter in our answer to nanometer. You should be able to do that by now. If you can't, Google it. Good luck. Oh, one more thing to add. Whenever you're calculating for the wavelength of the photon, keep in mind that is just for this first photon that you saw. So you'd have to repeat this calculation. You'd have to recalculate for a hypotenuse so that you can get the sine theta, because your theta angle is gonna change. You know, if you're looking way over here for your light source, that angle theta has definitely changed. So too will then the sine of theta. All right, that's all I've got. Hopefully that helps you for those of you that requested it. Good luck.